Hey, what's up YouTube? It's True again with another Cafe Yocto episode featuring a phyCORE-AM62x system on module and development kit. If you joined us in our last episode, we did a kit unboxing and then we did a quick start where we booted that development kit into Linux. Today's video is going to piggyback on that a little bit. I wanted to look at a little bit more about what happens between connecting power and you're getting a Linux login prompt and everything that happens in between those 2 points. So a lot of what we're going to cover today is actually out of this page of the technical reference manual from Texas Instruments here in this boot flow chart found on page 3933 of the AM62x technical reference manual for that 1.0 silicon revision. This is the one that's utilized on the alpha kit at this time of recording. So if you really want to know a little bit more about what's happening in depth, I would head over to the technical reference manual here. This is just a lot more information than we can really fit in a video. And to be honest, a lot of this is abstracted away by the fact that you are utilizing a phytech BSP and a system on module. For example, you don't have to implement your own DDR. We've done that for you. That's why you'd want to use a SOM. So this is really just good information for you to know. I'm going to give you some buzzwords to go look up things on your own here in the technical reference manual. So check this document out for more information. So let's get into the boot flow. So I have gone through this complicated guy and I've simplified it down quite a bit for myself. I'm going to go ahead and show you what I came up with. So this is not like an official boot flow. This is really True's hot take on how the boot process works on the AM62. So don't go to the bank with this information, but it's just to give you an idea of what's happening in a simplified view. Okay, so the first thing, when I connect power to the system on chip, which is the AM62 processor itself, that again is implemented on a system on module. A lot of terminology here floating around, just kind of differentiate and clarify what words mean what. So the system on chip, just talking about the processor. The first thing that happens when we connect power is the boot ROM is actually the first software to run on that guy. The boot ROM is read-only memory. It's burned at manufacturing from Texas Instruments, so it's not something that phytech has any control over. We don't change or modify it in any way. It comes on the chip. And that software is the first thing that runs, and the first thing it does is it actually pulls these boot mode pins. You could find these in the phytech schematics. We hooked these up to those dip switch banks that allow you to control the boot behavior of the system on module via pull up and pull downs. You can enable or disable those on each of these boot mode pins. And effectively, we can control where the boot ROM is going to look for its boot media. The SD card is configured by default on the development kit out of the box, but you could do other things like eMMC or potentially in the future network booting. Well, at the boot ROM level, it won't use network boot, but there's other options for boot. Essentially, you could store your boot device, boot binaries in various locations per your needs. Anyway, charging forward. So the boot ROM, after pulling the boot mode pins, will know to look at the SD card, and the first thing it's going to load is this TI boot3.bin secondary program loader. So this guy's going to bring up a number of subsystems within the processor, some security and system management related cores that are built on the M4 and R5 Cortex architectures. Anyway, charging forward, once the TI boot3.bin brings up the Cortex R5 device manager, it's going to actually be running from SRAM, this internal memory of the processor. That's because up until this point, there's no way of knowing what type of memory is hooked up externally, and that's the DDR memory. TI boot 3 is going to have knowledge of that. This is written by phytech, and the hardware, of course, is laid out by phytech on the SOM. So this will initialize that DDR memory. There's a little more room now. So this TI boot 3 is very small, and it can fit in the internal SRAM. Now that we have a little more external memory enabled, now we can load the secondary program loader for the Cortex A53s, which is our primary cores for the AM62 processor. And those now go ahead and load U-boot proper, which is our true secondary bootloader. So from the secondary bootloader, uboot.image, running on the Cortex A53s, that's going to go ahead and access the boot environment stored on flash memory, and that information is going to tell it where to go and load Linux. So from here, You could do network boot. You could give it information on what server is hosting your Linux kernel, what server is hosting your network file system. You could also load redundant binaries from various media. You could control all of that here in the bootloader. So this is really where users have the first opportunity to modify things on the fly without rebuilding anything. So once Linux gets loaded, now it's going to go through the device tree after setting itself up. There's a bunch of subsystems of the Linux kernel that have to be set up before we get into the hardware itself. So the device tree is a hierarchical definition of the hardware. It'll parse through that, and as it goes through it, you'll see like I2C gets set up. You'll see some Ethernet PHYs get probed and identified. The MMC interfaces are going to come up, and so that brings us to this last stage here, where the MMC interfaces, that's how we'd actually interface the SD card, the MMC, and that is going to give us access to the root file system. That's really going to contain the Linux distribution, all the user space applications, system services. That's all going to get mounted, initialized, and then you get user space. So user space is really this command line that we can access via the serial terminal, log in via root. This is user space. So that kind of breaks down in a nutshell the boot flow. Let's connect that up to the hardware and the software stored on the SD card, kind of connected to reality. So power off the development kit before you unplug anything. That's typically a good way to go. The reason is if we just disconnect power while the system is up, you could corrupt the SD card. Now, these in this Alpha 1 BSP for the AM62, phyCORE-AM62, this is using an ext4 file system format, so unlikely to corrupt it due to its journaling capabilities. It's not going to be corrupted if you just suddenly unplug power, but use your best practices whenever possible. Going to connect that SD card now to my host machine, and let's switch my screen. What we're going to need here in the next steps, we're going to need a Linux operating system. We'll get into this a little more in following videos, but here I'm using Ubuntu 22. It does not matter what a Linux distribution you're using for your host here. When we're just updating the SD card, taking a look around, any Linux host machine is going to work out for you. That's because we want to mount and view the Linux file system on the SD card. We can't do that in Windows natively. So I'm using VMware Workstation. I can go over here to this drop down, removable, and I can make sure that my SD card reader is connected to the virtual machine here. So now that I have my SD card, it's all mounted nicely. Let's go open those up. Let's take a look at the two partitions. So we got a boot partition and a root partition. The boot partition is going to contain those binaries we actually talked about already in the boot flow. TI-boot3, TI-SPL, and U-boot. You see that those are all included in the boot partition. And that's because actually the boot ROM can only access fat file system partitions. The Linux partition over here in root is going to be where our kernel binaries are all stored here in the boot directory. I almost confused myself. So this naming is a little confusing. You have a boot partition and a root partition. And in the root partition, we have a boot directory. And that's where the kernel binaries are all stored. So boot directory of the root partition. And here we got the kernel images. So this is just a symlink to this one with the version info. So you could have a number of these, and you could update what kernel you're booting just by changing the symlink. That's the point of that. And then we have the device tree binary. This describes the hardware to the kernel. So this is the primary one. You also have these DTB-Os. So this is a DTB. This is DTB-O. These are overlays. So these are like at runtime. We can modify the device, the hardware definition in the device tree. We can modify that at runtime just by adding or disabling these in the boot environment in U-boot. So these are all kind of targeting different add-on hardware. M.2 Wi-Fi module from Phytech, the OLDI, LCD, MIPI camera, and then this enables like a SPI interface. All right, so now that we've looked at all the binaries, let's walk through the actual boot process together and what that looks like. So make sure to safely eject your SD card again, just to prevent corruption. I'm gonna close those out and hop over to my board. SD card, plug that in, and connect power. should be getting our boot up, and I'm going to interrupt boot. So perfect. We already got some interesting stuff here. So we can see here the uboot SPL. I believe this is actually printed from the TI boot 3.bin, and it's going to start up a number of security cores. It's going to this is system firmware. This is another I can't remember which core this is, but all these early messages, not something that most of my customers will ever think about or worry about. So don't worry about this stuff. Version information, this is helpful to know which version of uboot you're running and the build date, the original one. This is a release image, so this is reflecting the release date of this BSP. Now getting a little further, we can see that the uboot proper is now started. So up until this this kind of prompt to stop auto boot, we're actually already up to here. This stages 1 and 2 happened very fast. DDR is already configured at this time, and so we could just go in and load the kernel. We could do that with boot, but first I want to take a look at the boot environment. We can do that with this print env command. I'm gonna make this a little bigger, and we can see here there's a number of things. This the way you would read this, right? When I type boot, it's actually the boot command that's run, and that's hard coded in the uboot binary. So it's going to run find FDT. So find FDT, that's actually specified somewhere here. And so this is actually going to get resolved, right? Set env name FDT to this guy. That guy's set right here. Look at that. That's the device tree binary that we looked at in the fat partition. So you can see how these scripts in the boot environment are essentially these nested variables. So it's I particularly like just saving the whole thing to a text file utilizing Control F. For example, if I want to know what boot part is, you could scan through here, but if you have a Control F, you know that boot part just resolves it too, and it's a lot quicker if you navigate things in like a text editor. But yeah, that's essentially how we could walk through any of these lines and resolve all these like components here that you set further down. The root partition is specified here in the kernel command line via the args mmc. Anyway, I think the big important thing is if you type boot, it runs this. And so we could do that now. It's going to continue on and load all the way into Linux. I'm going to scroll up while it does that. We can actually see the loading bar is still moving up. So it's still dumping out a bunch of activity here in the serial terminal. Once I type boot, though, we can just quickly confirm, look, that it's loading the kernel binaries. So loading device tree blob, DTB, that's what that means. And then it hands off execution to the Linux kernel. It's going to set itself up. So it's already actually running through the device tree early here. This reserved memory, this is all defined in the device tree. A bunch of clocks and all kinds of stuff. Now we're getting into the juicy bits. Let's see. Good example. There's a lot of subsystems within the kernel. So here, now we're getting an interesting hardware stuff. So I2C is now being brought up. So this is being parsed directly out of that device tree. CPSW. So this is the Ethernet controller for the PHY on the SOM. We also got these MDIO interfaces for probing the PHYs on the carrier board. Everything's being brought up. Now we can see this MMC is coming up. So shortly after MMC coming up, MMC 0. So this is the eMMC. We can see via these boot hardware partitions. But MMC 1 is the SD card, and shortly after having that come up, we need to confirm the size of the card here. Once that comes up, now we are mounting the root file system, and then we're loading system services out of it. So we can see the service names mentioned here. There's a lot of stuff. Just going to call out the good ones that I like. So there's a lot of stuff, which is an interesting one. Matrix GUI. So if you had your display connected up, you would have a Qt demo. That's all kicked off via this service here, and that starts regardless of this LCD being present or not. We can see again it's starting. Like TPD, this is like a network, a server, server stack. There's a service for that. let's see, multi-user. So this is actually the login prompt, and boom, here we are. So user space initialized. Yeah, and so that is the boot process here, in a nutshell. Total crash course. Let me know if you have any more questions.
Thanks for joining us for episode 2 of our phyCORE-AM62x Cafe Yocto series. Stay tuned for the next video, which is going to be all about exercising the phyCORE-AM62x. We will see you there.